This is a mini tutorial on restriction mapping, a standard AP biology problem. Typically, students are given a diagram of gel electrophoresis results that includes molecular weight standards, allowing them to determine the size of the different fragments generated by the enzyme digests, both the single and double digests. Students should add up the fragment sizes for each digest, and they should all be equal. This is the total plasmid size.
So as you can see, EcoR1 has a 70 and a 30 kilobase size fragment, which equals 100. For HAE3, there's a 40 and a 60 kilobase size, which is another 100. And then for the double digest, there's a 40, 30, 20, and 10, which altogether equals 100.
If the fragments don't add up, it is likely that there are fragments of the same size superimposed on the gel. That is, two fragments of 50 kilobases each will migrate the same distance on the gel and appear as a single band, even though there are actually two fragments of 50 kilobases present in that digest. So let's make a plasmid map. Start with a circle and pick one enzyme and put its initial site at 12 o'clock. Place the second cut at its correct position based on size. It's arbitrary whether this is the large or small fragment.
So as you can see, we've put the EcoR1 cut sites on the circle, and we arbitrarily just started with the 70 kilobase size fragment clockwise from the first E that is placed at 12 o'clock, and the second fragment is 30 kilobases.
Ask yourself if the smaller fragment is found in the double digest. If the answer is yes, then let's try to retain that fragment uncut. This means that the second enzyme will make both cuts in the larger fragment.
So as you can see, the 30 kilobase fragment is found in the double digest, so we're going to try to retain that.
By trial and error, place the second enzyme sites in the large fragment so that you get the appropriate sized fragments for the double digest.
So let's try making the first HAE cut site 40 kilobases from the 12 o'clock position. That leaves 30 kilobases in the larger 70 kilobase EcoR1 fragment. That then must be cut again into a 20 and a 10 kilobase fragment, so that we've got all of the fragments in our double digest, a 40, a 30, a 20, and a 10.
But while this means that we'll either have a 20 or a 10 kilobase size HAE3 single digest fragment, which doesn't work because we know those fragments must be 60 and 40 kilobases. So try again.
So what if we make our first HAE cut 20 kb from the 12 o'clock position? That would leave 50 kb to be cut in the remainder of this large 70 kb EcoR1 fragment. So we can make our second cut the required 40 kb from the first HAE cut, leaving 10 kb from the double digest. So now we have, reading clockwise, 20, 40, 10, and 30 kb fragments from the double digest. And our HAE single digest fragments are 40 and 60 kb in size.
In summary, starting at 12 o'clock with our EcoR1 digest, we have 70 and 30 kilobase fragments. Then starting at the first HAE3 cut, we have 40 and 60 kilobase fragments. And going clockwise with the double digest, we have 20, 40, 10, and 30 kilobase fragments. So I think we've solved the problem. There is another solution to this problem that makes only one cut in the larger 70 kilobase fragment and a second cut in the smaller 30 kilobase EcoR1 fragment. See if you can figure it out.